Hello, and welcome to Software Architecture Monday. My name is Mark Richards. I'm a hands-on software architect and also the founder of developer2architect.com. In this lesson, number 48, we'll continue with the reactive patterns of architecture and take a look at the Thread Delegate pattern. In lesson 46, I showed you that these reactive architecture patterns can be used to create self-healing and self-monitoring systems that can automatically repair and configure themselves. In this lesson, we'll focus on the Thread Delegate pattern, those event producers, dispatchers, and delegates. All of the examples I'm giving, you can find the source code for as well as demos by looking at my GitHub repo at wmr513/reactive. The Thread Delegate pattern really asks, how can we ensure timely and consistent response time as our system grows? And this is automatically without human intervention. If we acquire or merge with other businesses, if we happen to start growing our business, our systems can grow along with those without human intervention. This is reactive architecture. And in our roadmap of the Reactive Manifesto, this is where we have responsiveness and resiliency. As we grow, we won't fail, but we maintain that responsiveness. The Thread Delegate pattern looks as follows. We have an event producer that's sending events to an event dispatcher. And these could be orders, these could be trades, they could be claims, they could be requests for reports, any kind of business transaction. That event dispatcher picks up that business transaction and then delegates it to a Thread Delegate, hence the name Thread Delegate pattern. The dispatcher sends that message over to the Thread Delegate. That Thread Delegate processes that message. Now, it also has an internal queuing mechanism with that, and I'm going to go over that in a little bit. But that Thread Delegate processes the message. If a response is needed back to that event producer, it's up to the Thread Delegate to send that response back. For example, let's say that we have some sort of business transaction, an order that comes in, or a trade. The event dispatcher picks it up, and its only responsibility is to delegate it to a particular thread. That Thread Delegate processes that message, and again, if a response is needed back to that event producer, a confirmation number or an order number, it's up to that Thread Delegate to send that through another event channel so that the event producer gets that. And this allows systems, as I'm going to demonstrate, the ability to grow as our business grows. Now, there's a unique aspect also of the Thread Delegate pattern. Besides allowing businesses to grow, it also allows highly parallel, high-speed processing while preserving message order. You see, queues are FIFO, first in, first out. So, of course, I can dequeue messages in the right order. For example, 1 will always be dequeued before 2, but watch this, message 2 finishes before message 1. What if those needed to be processed in the same order? Let's take a look at how the Thread Delegate pattern allows this to happen. Because if we have a delegate, I can go pick up 1 and send that to a thread and pick up 2. So they're actually received in the same order, but alas, message 2 gets processed before message 1. How in the world can you possibly have dozens or hundreds or even thousands of event processors and still maintain the processing order of a message? So hopefully I have you intrigued, because this is the pattern of architecture to do that. Now, you might think that's impossible, and as a matter of fact, it is, without this premise. Because the premise is, and this works about 99% of the time, that not every message in the queue must be ordered, but rather messages within a specific context need to be ordered. Now, let me show you an example. In trading, we have this thing called trade correction or cancel rebooks. And so let's say I place a trade, a buy for Apple on that particular brokerage account of 2 million shares. I don't have enough, so that gets canceled, and I immediately rebook it for 1.8 million shares. Now, clearly, these 3 messages have to be in this order, 1, 2, and 3. However, this is what our trade queue looks like: a place for Apple, a place for Google, a cancel for Google, a cancel for Apple, a rebook for Apple, a rebook for Google. Now, these do not need to be in the same order. However, messages 1, 4, and 5 need to be in the right order. And of course, 2, 3, and 6 need to be in the right order. We can leverage this premise. Now, that context in this case could be in this case, it would logically be a brokerage account, but I'm going to show kind of symbols because it's a little easier. It could be a customer ID, it could be an order ID, whatever context. If we've got thousands of orders coming into our system, those orders don't necessarily have to be in order. Maybe it's the customer, or maybe it's the item, or maybe it's the order ID that has to be in order. Let's see how this actually works. So when we start thinking about preserving message order, we have the event producer coming to the delegate. What the delegate has in it is something called an allocation map. And again, if you go to my GitHub repo at WMR513/reactive, you'll see some code to actually implement this as well as some demos. A message comes in. The allocation map knows who's processing what kind of message. In this case, our context is going to be the symbol. Not a good context, by the way, but just for illustration purposes. Now, notice that queue on that thread delegate, or that event thread there. And so now, if an Apple order comes in, it knows that that event thread is processing Apple. If an order for Google comes in, it sends it to an event thread that happens to be processing Google. And this way, all of the messages of that particular context can actually be processed in order. As a matter of fact, we can actually use something called striping. So, for example, I'm going to stripe the symbol so that I can have hundreds or thousands of event delegates and still preserve message order. For example, all symbols A through M go through the top path, and N through Z go through the bottom. So, for example, across the top path, I can now ensure the order of all Apple trades, the order of all Google trades, and on the bottom path, I can ensure all of Spider Pharmaceutical and Spider Technology stocks, the XLKs. Notice I can stripe on the beginning of each symbol. Hence, I can have 26 event delegates, which then in turns has thousands of event threads. As a matter of fact, I can start striping on anything that starts with AA, AB, AC, AD, on, and I can have thousands of event delegates with thousands of threads. And you can start to see how this can scale to start processing thousands of messages concurrently in the right order. Let me show you how that preserved messaging order works. So what we have is the event dispatcher with an allocation map. Now watch this. It starts up event thread 1. So that's thread delegate 1. And notice the allocation map records that ID for that thread, or that object ID, and so or that thread ID, whichever implementation. And notice that there's arrows for a callback back to that event dispatcher. Now what that 0 is, in parentheses there, is the number of messages it's currently processing. So watch what happens here. A trade for AT&T comes in. It comes into the event dispatcher. The event dispatcher does a least used algorithm to basically say, who should I give this to? Because all 3 threads are eligible for this AT&T trade. Well, let's send it over to thread 1. Now watch what I do. As the event dispatcher, I update my allocation map. And by the way, if you look in the code, you'll see this is just a simple map. So I'm processing 1 message, so that's the count, and I'm currently processing AT&T. Now a Google comes in. Now we want all AT&Ts to be processed together, all Googles to be processed together. In this case, who's available? Well, 2 and 3 have the least used algorithm, so let's send it over to 2. Now notice the allocation map is now saying Google is being processed by thread number 2. Apple comes in, and now let's send it over to 3. What happens now? Watch this. Did you notice what just happened? 2 just ended. It calls back to the event dispatcher saying, hey, I'm all done. And so the event dispatcher said, okay, Google's no longer being processed. Notice the number of messages is 0. A trade for IBM comes in. Well, the least used algorithm, first of all, we check and say, is anybody processing IBM? Because those have to be in order. Nope. In other words, a place, cancel, rebook. No, so let's allocate it obviously to number 2 because that's the least used. Now things get interesting. Another Apple trade comes in. Now these are happening within several milliseconds each, everybody. And so this is very, 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 very fast. I'm obviously slowing it down. So the first question, is anybody processing Apple? Because that's our context. And all symbols have to be processed together. Yes. Number 3, and it's currently processing 1. So watch this. I send it over to its queue. Now this could be an external queue, or it could be an internal queue, like in the Java platform. This could be a java.util.queue. And now, watch what happens. Thread delegate, let's watch number 3 here. That finishes. It does a callback over to the event dispatcher. Notice it said, now I'm only processing 1 message. Now watch what happens to thread 3 there. Now it brings in that next FIFO ordered Apple stock. And now, number 1 finishes, it calls back to the event dispatcher. Number 2 finishes, and now we're in an empty state or a beginning state. It's a very, very powerful pattern, everybody, that allows highly parallel processing with message order. Now, if message order doesn't need to be preserved, then in this case, the allocation map is only going to contain the count. And what we want to do is start sending to threads, and once we maximize those threads, then we queue up, just based on a least used algorithm to kind of distribute the load. By the way, this is kind of the architecture pattern of how thread managers work, or connection managers actually work as well. Well, for more information, you can certainly go to Software Architecture Monday's landing page, which is on developer2architect.com/lessons, where every Monday I do provide a lesson in software architecture absolutely for free. And also, you can see where I'm coming up to talk about conferences or public trainings or even online trainings by going to my developer2architect.com/upcoming-events.html page. So this has been Lesson 48, the Thread Delegate Reactive Pattern. Again, my name is Mark Richards. Thanks for listening.